Hello friends, I'm myself Shruti, teaching in the IT Shop. So this is my fifth lecture in machine learning series. Uh, we are going to proceed for uh, principal component analysis. So for computing the principal component analysis, that's a unsupervised method of machine learning. We require to calculate the eigenvalues and the eigenvectors. So first we'll cover the eigenvalue and eigenvector. What is eigenvalue and eigenvector and how to calculate this. Then we'll be going for principal component analysis. So for eigen, again, I want to mention in my lectures, I've taken examples and different data from different sources included in my slide. So going for the eigenvalues and eigenvectors. Eigenvalues and eigenvectors are two quantities which represent my features uh, or the important characteristics of my features. So they are represented by an equation that is A V is equal to lambda V, where V is a vector. There's a difference between the scalar and the vector quantity. Scalar quantity is some numeric value that is 8 like that, and vector is it is a scalar quantity and with a direction. As force we are having a vector, so this I say is a vector. Vector has two values like 3 and 5, and this is what scalar quantity. So we have eigenvalues are the scalar quantities and eigenvectors are the vector quantities. So now we are going to calculate the eigenvalues and eigenvector. Another important thing is eigenvalue can be 0, but eigenvector can never be 0. So we can have eigenvector excluding the 0 vector, whereas we can have the value for lambda as 0. We'll see in the later slides. So the definition of eigenvector is it is a non-zero vector that also called the characteristic vector because this is giving me the characteristics of my features present in my data set. Uh, A is always, whenever we are going to compute eigenvector, then we require a square matrix. My data matrix must be square, and there exists a scalar quantity that is eigenvalue uh, that satisfies this equation. So, and scalar quantity eigenvalue can be 0, whereas eigenvector cannot be 0. So, let's say I want to show this 2, 1 is the eigenvector of this particular data matrix. So, what I need to do is I need to multiply this eigenvector 2, 1 with A matrix, and let's say my eigenvalue is 0. So if my eigenvalue is 0, so the right hand side part becomes 0. The right hand side part of my equation, that is lambda of x, this becomes 0, whereas the right hand part sides exist. So I can have eigenvector, I'll have some value of eigenvector even if I have lambda as 0. We'll do in the later example. Sorry. So will be now we'll see the properties of eigenvalue. As I said, eigenvalue is a scalar quantity. So for every non-zero eigenvector, as we said, the eigenvector is non-zero. For every non-zero eigenvector, this equation must be satisfied. If we take this TV left hand side, the equation will become the AV minus TV. If we take V outside, the equation will become A minus T IN. IN is nothing but is identity matrix. This is identity matrix. And if I if I say A minus T I N into V, this is equal to 0, which is having multiple solution, that is multiple values of eigenvalue, and the column of this are dependent, and this matrix is invertible. Invertible means we can't find the inverse of this particular matrix. If I find the determinant of this will give me the eigenvalues. So let's look how to calculate the calculation of eigenvalues. I need this equation determinant of A minus T I n is equal to 0. So for this, what I need is I need a data matrix that is minus 4, minus 3, 3 and 6. So this I have to take one identity matrix. So this is minus 4, minus 3, 3 and 6. Then I don't know the value eigenvalue. So this remains D, and I need to take identity matrix of same size of my data matrix. This is equal to 0, and I want determinant of this whole. So the determinant of this whole, I would say, is minus 4 minus D multiplied with 6 minus D plus 4 minus the 3 into 3, and this 4 becomes 0. So this gives me minus the 24, then minus of 60 plus of 40 minus plus of t square, and you get plus a 9 is equal to 0, and this gives me an equation of t square minus 2t plus, sorry, minus 15, this is minus 15 is equal to 0. So if I substitute t minus 5t, t square minus 5t plus 20 minus 15 is equal to 0. This gives me t minus 5 plus 3 t minus 5 is equal to 0, and this gives me the vectors t is equal to minus 3. So this will be t plus 3 and t minus 5 is equal to 0. So you'll get t as minus 3 and minus 6. So this is how you can calculate the eigenvalues. Now, corresponding to each eigenvalue, we require to calculate eigenvectors. So for calculation of eigenvectors, we say this equation, what we use for calculation of eigenvalues is determinant of A minus T in as a characteristic polynomial. And I need to make this characteristic polynomial is equal to 0. So if I make this characteristic polynomial equation as 0, this gives me the value of the eigenvalues. There are certain properties of eigenvalue. The summation of all eigenvalue is the sum of element of principal diagonal. This we see in later slides. The product of eigenvalues of matrix A is equal to the determinant. Definitely, we are calculating from the determinant, and lambda is a eigenvalue of matrix A. Then 1 over lambda is a eigenvalue of A inverse. Then is lambda is a eigenvalue of orthonormal matrices, where we have, I'll say, a matrix as an orthonormal matrix if I have A transpose is equal to identity. So this is the definition of orthonormal matrix. This you can cover in any mathematics book. So now coming to the eigenvectors. So let's say from this characteristic equation, we have found the eigenvalues as 1, 2, 3. Then going to the eigenvectors, how to calculate the eigenvectors. So for every value of lambda, we need to calculate the eigenvectors. So like first value we got is the lambda is equal to 1. And I assume my eigenvector is x1, x2, and x3 corresponding to lambda as 1. So if I substitute this, so what I have is my equation was, I have the equation that is A of V is equal to lambda V. And if I take this lambda V this side, this will become A of V minus lambda V is equal to 0. And I can make it A minus lambda I into V as a zero. So we are doing like this. So A into and lambda we are having is 1 here because my lambda is 1 here. So this is directly subtraction of the identity matrix. It's simply this is A minus the identity matrix. So if I do A minus identity matrix, I'll get this these values, and by this I'll form the equations that is x2 plus 2 of x3 is equal to 0, x2 minus x3 is equal to 0, and 2 of x3 is 0. So I know x3 is 0, and by this equation I can infer that x2 is equal to x3. So x2 is equal to x3 is equal to 0. I got, and I know by definition my eigenvector can never be 0. So because the eigenvector can never be 0, and I don't have any equations that will give me the value of x1. So I'll assume a value of x1 as k1. And because these eigenvectors, you won't get the exact values. You need to find the ratios of your variable. These vectors are the ratio of the variable. So my eigenvector corresponding to lambda 1 is 1, 0, 0, 1. I assumed x1 is some constant k1. So, and every variable present like x2 and x3, all the variables present in my vector, they are related to this particular one. So these x2 and x3 are k times of x1. So if they are k times of x1, then and we know that x1 and x2 and x3 is 0. So we'll be having the eigenvector as 1, 0, 0. Next eigenvector corresponding to lambda is equal to 2. For lambda is equal to 2, if I substitute 2 at the place of lambda, so you'll be having a minus 2i into x2 is equal to 0. So by this equation, if I solve this, I'll get the equations as minus of x1 minus of x2 plus 2 of x3 is equal to 0. Again, I'm getting x3 as 0. So if I substitute x3 0 here, so then I got relationship between x1 and x2 is x1 is minus of x2. So if again I assume x1 as k2, I assume x1 as k2, then x2 will get as minus of k2, and x3 I know it is 0. So by this ratio, I have x1 as 1, x2 as minus 1, and x3 as 0. Next, I calculate for lambda as 3. For corresponding to lambda is equal to 3, then my equation is a minus 3i. Now my equation becomes a minus 3i. So using this equation a minus 3i, I got two relationship between x2 and x3 and x1. So by this second equation, with the second equation, I can infer that x2 is minus of x3. So once I have x2 as minus of x3, so here I assume x2 as k3, and x3 will become minus of k3. Then now I can substitute the value of x2 in this equation, x2 and x3. So if I substitute the value of x2 and x3 here, so this will give me minus of 2x1 minus of k3, and this will become minus of 2k3. So this will give me minus of 2x1 minus 3k3 is equal to 0, and x1 is equal to 3 by 2 k3. I got, so x1 I got as minus ka 3 by 2 k3. This is minus ka 3 by 2 k3 because I'll take this in left hand side. So I got minus ka 3 by 2 k3. And because again I'm saying this is a ratio, so I may say this is minus of 3 by 2, or I may say x1 as 3 and x2 as minus 2 and x3 as 2. Both the way it is correct. So now I got the third eigenvector. After getting the third eigenvector, I will do for a 3 cross 3 matrix where there are no zeros. All values are 1. So in case of all values are 1, you will be getting all equations as true. So first I need to calculate the eigenvalues. For calculation of eigenvalues, I need to assume eigenvalue as lambda, and I need to calculate the determinant of this equation. So for calculation of determinant of this equation, if I calculate determinant of this will give me x cube minus the x cube plus 3x square equal to 0. X square I can take out, so lambda I got as 0 and lambda I got as 3. So for corresponding to these two eigenvalues, I need to calculate the eigenvector. So for lambda is equal to 0, this gives me three same equations. X1, X2, all will give me X1 plus X2, sorry, or XYZ is equal to 0. So what I need to do is I need to reduce this matrix, and by reducing this matrix, I'll get the relationship as x plus y plus z is equal to 0. So again, I need to make some assumption because from one equation, I cannot get the value of three variables. So what I'll do is I'll assume one unknown, one, because we are having three unknowns here. So I'll assume one value, like two values, y is equal to t1 and z is equal to t2. So if I assume y is equal to t1, z is equal to t2, x will become minus 3 minus t2. So again, I can say there's a relationship between T1 and T2. T1 and T2, they both are, we are having, we can have T1 is equal to minus of T2, or T2 is equal to minus of T1, like this kind of relationship you can have. So corresponding to these two, we are having two eigenvectors. One is the minus 1, 1 and 0. Another one is minus 1, 0 and 1. Corresponding to one uh, single eigenvalue, that is 0, we are having two eigenvectors here because we have two possibilities in this. Then corresponding to 3, then again we are having three equations. Again, we'll be getting three equations because all the values in my matrix are non-zero. All my values are non-zero. So what I need to do is I need to reduce this matrix to the upper triangular matrix. Once I get the upper triangular matrix, then I can solve. So this is my upper triangular matrix. Then I have the relationship between two variables. So I got a relationship between two variables is I got y is equal to z by this particular equation. So once you have y is equal to z, you can assume any either y or z. So if I assume Z as T, then I can substitute uh, T in this equation. So after getting T in this equation, I'll get Y is equal to Z is equal to T. And now if I substitute T here, then this will give me 2 of X is equal to minus the 2 of X plus 2T is equal to 0. So you'll get X is equal to T. So again, if I say the ratio by the ratio, my eigenvector is 1, 1, 1 corresponding to eigenvalue 3. So corresponding to eigenvalue 3, I have eigenvector as 1, 1, 1. Corresponding to eigenvalue 0, I got two eigenvectors, that is minus 1, 1, 0 and minus 1, 0. So this is how we can calculate the eigenvalues and eigenvectors. We have a practical implication of these eigenvalues and eigenvector using this eigenvalue and eigenvector. If you are having a large eigenvalue, that means this gives you more variation in the data. So you can expand your image by putting the higher uh, value or higher scaling your um, eigenvalues, or if you are having a smaller eigenvalue, using the smaller eigenvalue, you can shrink your image. So you can do the compressions or expansion of image by using this eigenvalue and eigenvector. Another use of this eigenvalues and eigenvector, this can be helping, these vectors can be help you in the image rotation. If you rotate your eigenvector by certain angle, this will give you the image rotation. So we are using this eigenvalue and eigenvector in the face detection task or for identifying important characteristics of the face or in image rotation or transformation, different tasks. So this is all about the calculation of eigenvalues and eigenvectors. If you have any doubts, please do comment to me. And if you like my videos, please hit the like button, subscribe me, and share to your friends. Thank you very much for this video. I'll be covering principal component analysis in my next lecture.